Okay, let's start. Today we are going to talk about properties of the determinant. Where are we now? In previous lecture here. So we introduced the determinant, right? So what was the determinant? So determinant of the 2 by 2 matrix is something like this, right? So when matrix A is defined A, B, C, D, then the inverse of the matrix is something like this, right? In here, AD minus BC is equal to determinant of A. Okay, so this is the determinant of the 2 by 2 matrix. Actually, we already know how to do this, but uh, in this section, we introduce the more general version of the determinant of the larger scale matrix, right? So how can I do that? So from 3 by 3 matrix, we we derive the determinant of the 3 by 3 matrix, right? So here this triangle, it was the determinant of the 3 by 3 matrix A, right? Then then we found that this 3 by 3 matrix, the determinant of 3 by 3 matrix can be estimated by the sequence by the summation of the 2 by 2 determinant of a 2 by 2 matrix, right? So it means that we can recursively estimate the determinant of the larger scale matrix, right? So here, right? So in general, n by n determinant is defined by determinant of the n minus 1 by n minus 1 submatrix, right? So this is the way to estimate the determinant of larger scale matrix. So yeah, here was the definition. So the determinant of the general n by n matrix A here is the sum of the n terms of the here plus minus a1j determinant large a1j. Okay, so this is the definition of the determinant, right? So yeah, so by using this one, we can estimate any kinds of the determinant of the matrix, arbitrary matrix. Okay, so this is the one example. To generalize this computation, we introduced the cofactor, right? So what was the cofactor? So the cofactor I comma j cofactor of the matrix A is defined something like this, right? So by using the definition of the cofactor, we can represent the determinant of the matrix A something like this, right? So this formula is called the cofactor expansion. Cofactor expansion across the first law of A. Okay, so by using the concept of the cofactor, we can generalize the computation of the determinant. So yeah, here is the general rule. So the determinant of the n by n matrix can be computed by cofactor expansion across the any row or any column. So by using the any row, we can estimate the determinant of matrix A, or by using the any column, we can estimate the determinant of matrix A, right? So in other words, if there are easier rows or the column, then we can fix those kinds of rows or column to compute the determinant. So it means that if some rows or some columns contain zero values, right? Then we don't need to compute those kinds of term related to the zero values. So we can improve we can reduce the computational time to estimate the determinant. So for example, so here rather than using this first law, by using the third law, we can reduce the computational complexity for this term and this term, right? So by using the cofactor expansion, so we can pick the most easier rows or columns to compute the determinant. Okay, so before that, we also have to know the sign of the cofactor, right? So um, here, right? So we have to notice that the sign of the cofactor is not depend on the sign of the a aij itself, but the position of aij in the matrix. So, for example, in here, the a11, the sign of the a11 is just plus, and sign of the a12 is the minus. So we can determine the sign of the cofactor depend by 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 depending on the position of the aij in the matrix. Okay, so here's one more example. So to compute the determinant of the something like this, rather than using the previous one, we can use the cofactor expansion, then make the they make the computational determinant easier. So here we first use this one and this sum matrix, right? So by using this, we don't need to compute this one, right? And then we can do similar thing again. So here and here, finally, determinant of matrix A is the 3 times 2 times 2 times determinant of this very small matrix, right? So we can easily find out the determinant of A, something like this, right? So to summarize, so we can, if the matrix A is the triangle matrix, then determinant of matrix A is the product of the entry on the main diagonal of the matrix A. So something like this, right? So actually, if you see this matrix, actually this is the echelon form of the arbitrary matrix A, right? So we can say that, okay, there was the arbitrary matrix A, something like this. Then this is the echelon form of this original matrix, right? So rather than computing the determinant of this original matrix, because the original matrix are very complicating, so then rather than estimating this one, but if we can use the determinant of this one, then we can accelerate the computational time to compute the determinant of the original matrix A, right? So today we will talk about how can we use the low reduction algorithm to determine the determinant of the original matrix A by using the determinant of the echelon form of the original matrix A. Okay, so today we will talk about this. Okay, so let's start. Yeah, let's start. So yeah, today we will use this theorem, the law operation theorem. So we already discussed law operation that consisting of the three things. Okay, if we go back to the lecture 5.3, no, lecture 6, yeah, here. There was a 3 elementary matrix. First one is the replacement, and second one is the interchange, and third one is scaling, right? So you already know what those kinds of matrix means, right? So if the multiple of the one law of A is added to the another law to produce the matrix B, then determinant of B is equal to determinant of A, right? So the first one is what? The first one is replacement, right? So replacement. So in other words, if we apply the replacement operation to matrix A, then the determinant of the output matrix is equal to the determinant of the original matrix A. Okay, so this is the first theorem. The second theorem is that if the two rows of matrix A are interchanged to produce B, then determinant of B is equal to negative determinant of A. Okay, so this is the interchange, right? So this is their interchange, right? Then finally, if one row of matrix A is multiplied by constant value K, then determinant of the output matrix B is equal to K times determinant of A. So this is the scaling, right? So scaling. Okay, so in other words, if we apply the row operation, something like replacement, interchange, and scaling, then the only difference of the determinant of original matrix and output matrix here. If we apply the replacement operation, the determinant should be same, right? It means that there is the one times determinant of A, right? Then and if the interchange operation were applied, then the only difference is the negative 1 times determinant of A, right? Then if the scaling operation is applied, then the only difference is the K times determinant of A, right? So actually, it is really hard to prove this theorem in a systemic manner, but in the end of today's lecture, we will just see the what's the meaning of this theorem. But before that, let's just use this theorem to derive the new way to estimate the determinant. Okay, so let's start. Okay, so the first example is that we need to compute the determinant of A, well, where matrix A is equal to something like this. Okay, so if you remember our previous lecture, in lecture 8.1, there is some rule, something like the cofactor expansion, right? So we can also use this cofactor expansion for estimating determinant, but today we will just use this theorem. Okay, then let's do that. Okay, first of all, determinant of matrix A can be represented something like this, right? By using this one, right? This notation, right? So first of all, we already know replacement operation cannot change the determinant of the output matrix, right? So it means that determinant of the original matrix is same as this one. This is the low reduced output matrix from here. Okay, so from original matrix we can eliminate this one, right? by using the replacement operation, right? So the here, right? Then what do we want to do next? We also want to use we also want to reduce this one, right? So here, right? So determinant of this term will be exactly same as the determinant of this one, right? Right? And then what do we want to do next? Because we want to estimate we want to derive the row reduced matrix or the echelon form of the matrix, right? Because if we have the echelon form of the matrix, then we can easily find out the determinant by using this theorem in the previous lecture, right? So what do you want to do next from here? We want to replace this row and this row, right? So we have to apply the replacement operation. So here, right? So by using the interchange operation, right? So by using the interchange operation, we have to consider the -1, right? On the previous determinant, right? So the final one is the negative determinant of this echelon form, right? Okay, now we have the triangular matrix, right? Then what is the determinant of this triangular matrix? Product of the diagonal term, right? So finally, -1 times 1 times 3 times -5. So it is equal to the 15, right? Let me see. Oh yeah, 15, right? Okay, so by using this theorem, we can easily estimate the determinant of the complicated matrix, right? Okay, so let's do the more difficult one. Okay, we have a matrix with size 4 by 4, right? Something like this, right? And let's compute the determinant of matrix A, right? Then how can we do that? We can use the cofactor expansion, right? Here, but here we will use the row reduction algorithm or the elementary matrix to derive the echelon form of the original matrix, then find out the determinant of the original matrix A, something like this. Okay, let's do that. So we have to find out the echelon form of this original matrix A using the row operations, right? Okay, let's do that. First of all, because there is the 2 and 3 and -3, so if we have the 1 here, then the computation would be much easier than using this value 2, right? Because if we use the value 2, there might be some floating value, something like the 1 point blah blah blah, 2 point blah blah blah, something like this. So first of all, let's reduce this one as just 1. Okay, so what are we going to do? Actually to make this one as a value 1, then we have to use the scaling here, right? So scaling. So if we apply the scaling operation, the determinant of the output should be k times determinant of A, right? So in other words, determinant of A is equal to k 1 over k times determinant of B, right? Okay, so to from here we make this one something like this by using the 1 over by using the multiplication of 1 over 2, right? Then there would be one constant value in front of that, right? So this is the first step, and then let's remove this one, right? We can eliminate this term by only using the replacement operation, right? So because the sequential of the replacement operation does not change the determinant, right? From this theorem, right? Then the determinant of this one will be exactly same as this one, right? Then what I want to do next, we want to remove this one by using this one, right? So it will be something like this, right? Then something like this, okay? Okay, now we have the echelon form of the original matrix A. Then we can easily find out the determinant, right? Then what is that? 2 times 1 times 3 times negative 6 times 1. Okay, so it will be negative 36, right? Okay, so if we don't know this theorem, we have to find out determinant of this complicated matrix by just using the cofactor expansion, which will be really time consuming, but by using the row reduction algorithm and the property of the determinant of the elementary matrix, that we can improve the computational complexity to estimate the determinant. Okay, so this is the much easier way to find out determinant. Okay, so let's summarize what we are doing so far. Suppose square matrix A has been reduced to the echelon form U by row replacement and row interchange operation. Actually, this is always possible since we do not need row scaling to obtain the echelon form. If we want to estimate the reduced echelon form, we have to use the row scaling. But by only using these two operations, we can estimate or we can obtain the echelon form. Okay, and then because this row replacement cannot change the determinant, right? So the only difference here, with the low interchange, right? So let's say there are interchange, let's say 2 interchange or 3 interchange, then we can say that determinant of the original matrix A is equal to negative 1 superscript R times determinant of U. Okay, so from here, right? So in other words, let's say we have a matrix A, right? Then by applying the row reduction algorithm, we finally get the this echelon form matrix U. So let's say there are two kinds of case. The first one, so the first case is they have the pivot position on every rows, or there might be some zero values, right? So in this case, determinant of u is not equal to 0, right? Because the determinant of u is the product of this term. This square represent the non-zero value, right? Then what about this? Because this one, determinant of u is equal to 0, okay? So in other words, determinant of u here, determinant of u is depending on this one or this one. In other words, if we have the echelon form of matrix A, something like this, then the determinant of u would be negative 1 superscript r times product of the pivot in u here. But if the echelon form of the matrix A is something like this, then their determinant of u is just 0, right? So because of this term, right? So in other words, in this case means this matrix is invertible, right? Then this case means this matrix is non-invertible, right? So to summarize, if the matrix A is invertible, the determinant of u defines something like this, and matrix A is not invertible, the determinant of u something like this. Okay. So from here, we have the very important theorem. Let's say square matrix A is invertible if and only if determinant A is not equal to 0. Why? From here, right? So if the determinant of matrix A is not equal to 0, then there's they have to have the pivot position on every row, right? So it means that it is the invertible matrix. Why? Because of the here invertible matrix theorem, right? So if you remember what the invertible matrix means, if A is the invertible matrix, then A has the n pivot position, right? So in this case, if A is invertible, then determinant A should not equal to 0, right? In other words, determinant of matrix A is equal to 0, then square matrix A is not invertible. Okay, so this is the theorem. Okay, so actually this theorem adds the statement determinant A is not equal to 0 to the invertible matrix theorem, right? So in other words, if the determinant of matrix A is not equal to 0, then we can say that, okay, this matrix has this property, right? This kind of property. Okay, it's amazing, isn't it? Okay, I mean, if we can find out the determinant and see determinant of matrix A is equal to 0 or not, then we can understand the action of the matrix A, something like this, because they are whole equivalent, right? So this is this is why we we introduce and run the determinant of matrix A. Okay, so this is the determinant using the echelon form, right? Then useful corollary is that determinant A is equal to 0 when columns of matrix A are linearly independent. So what does it mean? So if the columns of the matrix A are linearly dependent, then if you go back to the lecture 8.1, no, where is that? Okay, let's see. No. Where is that? To introduce this one, we have to open the lecture. Maybe here. Yeah, here. So it means that the columns of matrix A does not form the basis of the Rn space, right? From the lecture 7.2, then we can say that the matrix A is not immutable, right? Because from the immutable matrix theorem, right? Then from here, we can say that determinant of matrix A is equal to 0. Okay? So determinant of matrix A is equal to 0 is equivalent to the columns of matrix A are linearly independent. Okay? This property also can be applied to the rows of the matrix A. In other words, determinant of matrix A is equal to 0 when the rows of the matrix A are linearly dependent. Why? Because the rows of the matrix A are columns of the A times, right? Because if the matrix A is something like this, and matrix, okay, let's throw something like that, and A transpose is something like this, then the rows of the matrix A will be columns of the A transpose, right? Then the linearly dependent columns of A time A transpose, linearly dependent columns here, make the A transpose not immutable. A transpose not immutable, right? Because the linear dependent and immutability is the equivalent, right? From the this immutable matrix theorem, right? Then when the A transpose is not immutable, so is the A. It means the A is also not immutable. Why? From here. From A transpose is not immutable matrix, is an immutable matrix is equal to A is the immutable matrix. Okay, so to summarize, the columns of matrix A is linearly dependent, or rows of the matrix A are linearly dependent, then we can say that determinant of matrix A is equal to 0. Okay, so let's see the example. Okay, so we have a matrix A, something like this, right? So, okay, so to find out the echelon form of this matrix, let's add 2 times row 1 to the row 3, okay, right? So, to reduce this one, right? Then we get these 2 rows, right? So, these 2 rows are exactly same here, right? So, what does it mean? What does it mean? The columns of the matrix A are linearly dependent, right? Because the rows of the matrix A are linearly dependent, then we can say that determinant of matrix A is equal to 0. Okay, so the columns the columns or the rows, because the here the rows of the this one are linearly dependent, right? Right? Why? Why in here they are linearly dependent, right? Okay, let's say this is the R1 and R2, R3 and R4, right? Right. So let's say 0 times R1 plus R2 minus R3 plus 0 times R4 is equal to 0. Why? Because R2 and R3 is exactly the same, right? So in other words, 0, 1 here, right? 1, negative 1, 0 is the solution, or the 0, 1, negative 1, 0 the coefficient that satisfy these vector equations, right? So which means those row vectors are linearly dependent, right? So if they are linearly independent, the only the kinds of coefficient should be zero vector, right? But in this case, it's not a zero vector, so they are linearly dependent. So what does it mean? Because they are linearly dependent, we can conclude the determinant of matrix A is equal to 0. So in this case, determinant of the matrix A is equal to 0. Okay. So this is a way to estimate the determinant. Okay, let's do one more example. Let's say we have a matrix A, right? So provide for matrix A, then let's find out the determinant of matrix A. Okay, so let's do that. So what should we do? First of all, we have to row reduce this original matrix, right? Then how can we do that? Because this term is 0, right? So we have to replace this row 1 and row 2, right? Then derive the echelon form of the matrix A, right? But as you can see here, it might be some additional computation. So I mean, if we can simultaneously use the cofactor expansion based method in the lecture 8.1, something like this, and the row operation based method that are discussed today, then we can accelerate the computation of the determinant. So what does it mean? Okay, so rather than using the replacement operation here, let's just use this one to eliminate this one first, so we can get this matrix, right? Then from here we can use the cofactor based method here. Why? Because in this column they are all 0, right? So it means that by only considering this term and this matrix with the negative sign, because the position here is the 2, 1, right? So negative 2 times the determinant, this one, it will be same as the determinant of the original matrix A. Okay, so So what are we going to do next? From here, now we can row reduce this one, right? How? By eliminating this term, and then what are we going to do next? We have to replace these two rows, right? But as we discussed previously, from here we can just use the cofactor based method by using this term and this submatrix, right? So negative 2 times 1 times the determinant of this one, right? Then what is that? This is just 15, right? So this is the negative 2, right? So finally it should be negative 13, right? So this one. Okay, so from here we can think of several things. First of all, we can apply the row reduction algorithm directly from here, then estimate the determinant, something like this, right? But if we can use the cofactor based method, then we can reduce the unnecessary computation, right? So please compare the which one is better yourself, okay? So this will be the very interesting finding that you can do, okay? Okay, so today we've talked about how to compute the determinant by using the row operation, right? So finally, there's one more theorem. If the matrix A and matrix P are n by n matrix, then determinant of the A times B is equal to determinant A times determinant B. Okay, this is called the multiplicative property. Okay, so actually there is some proof to there is some description to prove this theorem, but in here let's just verify this theorem for very simple case, 2 by 2 matrix case. Okay, so let's say matrix A something like this, matrix P something like that, right? Then matrix A times B is equal to this one, right? So what is the determinant of A times B? Will be 45, right? Then what is the determinant of A here? 9, right? Then what is the determinant of B? 5, right? So determinant A times determinant of B is equal to 45. So which will be exactly same as determinant A times B. Okay, so this is just very simple verification, but I think this is enough to understand this theorem. Okay, so by using this theorem, we will reformulate this one. Okay, so today we just used this one. Then from now on, let's find out the meaning of this one. So okay, by using this property, we can reformulate the theorem, row operation theorem, something like this. Let's say we have a matrix A with the n by n matrix, and elementary matrix E is an n by n elementary matrix, right? Then the row reduction algorithm is just the sequential multiplication of the elementary matrix, right? So if we just one sequence of the elementary operation or the row operation, then this is just the E times A, right? So the definition of the E is in lecture 6, right here. So please understand what those elementary matrix means in the lecture 6, right? So here, determinant of the elementary matrix times the original matrix A is equal to the determinant of matrix E times determinant of matrix A. From this theorem, this multiplicative the property theorem, right? Okay, then what is the determinant of the elementary matrix? There is three kinds of things from here, right? So 1, -1, and k, right? So if the E is the row replacement, then determinant of E should be 1, right? Then if the E is an interchange operation, then determinant of E should be -1, and determinant is the scale by R, then determinant of E is equal to R. Okay, so this page is exactly same as our first page here, right? So let's prove this one. Okay, so first of all, what is the determinant of the row replacement matrix? Okay, if we go back to the lecture 6 here, okay, what is the determinant of this matrix? If you remember the this one, if you remember this one, we can easily derive the determinant of the, where's that? Yeah, determinant of this matrix is just 1. Why? Because the determinant of this matrix is just the product of the diagonal term, right? So the diagonal term are whole 1, so the product of those diagonal terms will be 1, right? Okay, we prove this one. And what about this? What about this matrix? The product of the diagonal term is what? K, right? This is very intuitive, right? Okay. In this case, this is R, right? Then, what about this? What about interchange? Actually, the interchange can be derived by the row replacement. What does it mean? Okay, let's say we have a matrix A, then there is some rows I and row J, row I and row J, right? Then by using the interchange, we can find out Rj, Ri here, something like that, right? Then let's derive this one by using row replacement and scaling. So how can we do that? If we add this row and this row, which will be Ri plus Rj and Rj, right? Then if we subtract this one and this one, then Ri plus Rj R minus Ri, right? then if we add this row and this row, then Rj and Ri, right? Then finally, if we use the descaling operation here, then we can finally get this one, right? So by multiply -1 on this row, right? So this one will be R, right? So in other words, this interchange operation can be decomposed to the several kinds of the row replacement with the scaling term, right? So in other words, because there is only one difference here, -1, so we can say that the determinant of E for the interchange is just a -1. Okay, so this is very intuitive proof. So actually it's not a systemical way to prove this one, but I think it's enough to understand what to understand this meaning. Okay, so if you are more interested in the proof, please see the textbook, our textbook, but you can easily understand this property. Okay, so in other words, by using this theorem, we can easily find out the determinant of the arbitrary matrix A by using the cofactor factorization in lecture 8.1 and row operation based method in lecture 8.2, today's lecture, right? So yeah, now we can estimate the determinant of the arbitrary matrix A. Okay, so in this week we just introduced the concept of the determinant, right? So actually the determinant is the very important concept, and they have so many theorems, but we just introduce the very few theorem for the determinant, but I think this kind of theorem is enough to derive our following concept, something like the eigenvector or some singular value decomposition thing, something like that. So please try to recap our lecture 8.1 and 8.2 to move on to our following lectures from next week. Okay, this is the end of today's lecture. Thank you.